Let's just take a two-dimensional shape, right, like this. And let's take a piece of it here. Okay, so we want to find the moment of inertia of that in cylindrical coordinates. This one is going to be much better doable in cylindrical coordinates than in regular rectangular coordinates. You take a little piece of the disc here, okay, and it's rotated about like this. So what ends up happening is, depending on where the disc is, where the little piece is, the distance that it has to go around is farther, right? So what's the moment of inertia of that little piece? Di is equal to what? Well, its horizontal distance from the axis of rotation is x squared, right? And then we multiply that by dm. So it's much better to do this integral again in cylindrical coordinates, right? So what we're going to do is dm is going to be sigma dA. We are focusing here more on the surface, just the two-dimensional surface, rotated about the axis, cutting it in half, right? So we put sigma dA, and then dA, since we're using cylindrical coordinates, is r dr d theta, right? So now we have to relate x to r. Well, since this is here x, and this is r, what's the relationship? So we have x, we have r, that little piece. This is x, okay? This is theta here. So this is theta. So since x is the horizontal component of the r, right? So it's just the distance of the little piece from that axis. So x is equal to r cosine theta. Okay? So then we input that into our x here. So we have di is equal to r squared, and then since it's cosine theta, we're going to have cosine squared theta, and then we're going to have sigma r dr d theta. So now we're all set to integrate this. We do the integral, and you have I is equal to, we're going to do a double integral in terms of r and theta. So we're going to, sigma is going to come out of the integral, then you're going to have r squared r cubed dr d theta, and r goes from what? 0 to the radius of the circle, and theta goes from 0 to 2 pi, right? So of course we have the cosine squared theta. We're going to bring that in later on. So what is the integral of that? We have r to the 4th over 4, right? So we have I is equal to sigma integral 0 to 2 pi, and we have r to the 4th over 4, just like we had before. Then we have cosine squared theta d theta, okay? And we're integrating this from 0 to 2 pi. This is actually a pretty common integral that appears in calculus. Whenever you integrate cosine squared theta d theta from 0 to 2 pi, or you could even do sine squared theta d theta. This is a common integral, and when you go through the steps, it's going to take a couple steps to get to the actual answer, and you're going to actually get pi, okay? As a matter of fact, we use this in electricity and magnetism. When we do AC circuits, we say the integral 0 to 2 pi sine squared theta d theta divided by 2 pi is equal to what? This is the average value of an AC circuit in a circuit, okay? And this actually comes out, this top value comes out to be pi, and you divide it by 2 pi, and you get 1/2. You could watch my videos on the chapter 33 of the book, in a chapter on AC circuits, and I go through this actual integral and I show you that. So we're going to use that result now, and moment of inertia xx is going to equal sigma r to the 4th over 4. Integral cosine squared from 0 to 2 pi is pi. We are very close to our final answer now. So once you do that, then you get what? Sigma is the surface mass density, and that's equal to mass over area, which is pi r squared, times r to the 4th pi over 4. And what is that equal to? and pi cancel, r squared, r to the fourth cancel, mr squared over 4. Okay? Notice IZZ came out to be what? mr squared over 2. So therefore Ixx is half of IZZ. Okay? So now that proves for you the total moment of inertia of a cylinder equation. So now we're going to go to the moment of inertia of a sphere.